Hi class, we're now on chapter 9.3. This is the electromagnetic spectrum. So I previously discussed this in the previous section, but now I'm going to focus on it a little bit more to help you understand it. This picture is reversed from the other one. This one has high energy on this side and has low energy on this side. But what this mainly focuses on is the visible light. So this is electromagnetic radiation. Our eyes can only detect this small sliver here, but we know that everything else exists. You know, we've taken x-rays and people protect themselves because of those x-rays when you're in that room. Ultraviolet, UV, is something that we put sunscreen on to protect our skin from. So even though we can't see it, it's still there. So this is the entire spectrum, and we have short wavelength, high frequency, radiation on the right and left. So let's take a look at here. Here is high energy. That means short, small waves. So this is high frequency equals high energy. Low frequency equals low energy and big waves. So as we go from radio waves to microwaves to infrared to visible light, UV, X-rays, and gamma rays are the highest energy. Invisible is somewhat in the middle, and it's a very small portion compared to everything else. And even the colors again. Red is very low in color, in value, in wavelength of energy compared to violet. Now see these numbers? They actually, so even though this is a large value, it is actually the opposite of what we want it to be. This is a high value in comparison to 400, but it also is a lower energy. So the bigger the number, the lower the energy if you look at these nanometers. So 400 is the lowest, that's the highest energy, and everything else is in between. Okay, so this is again another chance of looking at an electromagnetic spectrum or radiation. Either one is the same thing. So this is all light, but they're different wavelengths and frequencies, and you can think of these as a fingerprint for that wavelength. So for instance, if we go back, red is going to be in the 750 to 700 range. You're never going to, in nanometers, you're never going to see blue with a value of 750 to 700. It's going to be between 500 and maybe 425. It's going to be here. So it's a fingerprint. That's the color you will see with that value. Longer wavelengths are associated with lower frequencies and lower energy. So this is radio and microwaves. Shorter wavelengths are associated with higher energy, higher frequencies. Think of X-rays and gamma rays. Okay, so now if we look at the visible, this is breaking up the waves itself. So you can see waves. So even the colors here, I had that little prism on the other page, other section, that you can see the difference in the waves. So you can see radio is kind of just a line or a slope, and then microwave starts curving more. In infrared, you get a curl, and in visible, we get more curls, and then it just gets into a spiral until it's just tight curl here. So there are 7 regions: radio, microwave, infrared, which is IR, visible light, ultraviolet, which is UV, X-ray, and gamma. And again, the frequency and the wavelength of light are inversely proportional. So as frequency increases, the wavelength decreases because you want small waves. So that's what these arrows you can see: increasing energy, increasing wavelength. And you got to be careful of the terminology. You might be thinking of something else when it's actually asking for a different definition of whatever that term is. And we'll show you that right now, what I mean. As frequency decreases, the wavelength increases. So this is something to understand. If wavelength increases, that means it's lower in energy, and the frequency decreases because you're getting larger waves. So here is, you can see, if you look at even the spectrum, you can see that the waves here, the purple, are a lot tighter than what the red is. Those are more like little mountains, where this are just really, it's more of a spiral. Now, here's one thing I want to point out. Do you see this is 400, this is 700? Do you see this is 750 and 380? Everything you pull in a chemistry book is off a little bit, and I don't know why people can't stick with just the same numbers, but you should definitely know the range. So 400 to 700 is usually the good one to get stuck in your head, and then you can separate what these are. But I will not give this to you. These are something that you would just have to know. You can see here that the colors, though, even though the numbers are slightly off, they do still match up pretty well for you to have an idea of what is what. So red being the lowest energy, and violet being the highest energy on this spectrum. And you can see down here, if you needed more confirmation, it says it right there. And this is in nanometers. Okay, so this is a slide that I had from the other section. I'm bringing it up again because I want you guys to be comfortable with this and understand this. As we start going more into this, it's easier to understand if I just keep throwing this slide into your face. Wavelength is lambda. It is the distance between two corresponding points on the wave. Frequency is the number of crests that pass a given point per second, and it's also known as hertz. Frequency times wavelength equals a constant. But when we start messing with numbers and values, this is where they start being inversely proportional to each other, because this value doesn't change. So these have to adjust for that. All right, so let's do a little bit of testing here. Arrange these types of electromagnetic radiation in an order of increasing wavelength. First, this is what I'm talking about. You might be thinking energy. Okay, well, what is wavelength? If it's asking for increasing wavelength, that's smaller, lower energy, because wavelength has to do with the bigger the wavelength, the lower the energy. So I want to make sure you're understanding what the definition is and not get something already stuck in your head. So increasing wavelength is this, bigger, lower energy, not this. So we have visible, which is here. We have X-ray, which is here, and we have microwaves. So this is an order of increasing wavelength. So this is from small wavelength to big wavelength is what it's actually asking for. So let's take a look what we have. X-rays have the shortest wavelength of the three. So it's going to be the first one you put with the little arrow. Visible will be the next one, because we're actually going in order of this. So X-rays, then visible, then microwaves, because microwaves have the biggest wavelength, the lowest of the energy of these three, the less frequent. So this means smallest amount of wavelengths to pass a set point in a specific amount of time, because they are larger wavelengths. So the larger the wavelengths are going to take longer to pass through than something small. All right, arrange these types of electromagnetic radiation in order of now increasing frequency. What's frequency? This is energy. So it's asking for increasing energy. That means smaller wavelengths. So again, we have visible, X-ray, and microwave. So if we look at these, microwave is here, visible is here, and X-ray is here. So if we're going this direction with the higher frequency and shorter wavelengths, then it's going to be microwaves here, visible, and X-rays. This is in order of increasing frequency, energy. Arrange these three types of electromagnetic radiation in order of increasing energy per photon. So I said in the last section, these were electrons. These are light packets, and I actually fixed that on the Canvas page. I put the definition. These are light. This is just light. But the light per photon can have, depending on where it is, can have more energy than others. So in here, in order of increasing energy per photon. So this means that the higher the energy, the more photons are going to come out of this compared to something with lower energy. So this is still energy. That's what this is basically stating. So if we look at this, microwaves has the lowest energy, and here's the arrow for increasing energy. Visible, then X-rays. So energy per photon decreases with increasing wavelength, but increases, I don't know why I'm saying that, increases with increasing frequency. So this is still, even though it's a fancy energy per photon, this spectrum is energy. So look at where its highest energy, and that's going to have more energy per photon than what's something that's smaller. That's it.